Hey, what's going on, folks? It's Mike here, and welcome to my next lesson in the software design series. In this lesson, we're going to be doing the implementation of the strategy design pattern. So if you didn't see the previous video, go ahead and check that out just to see and understand where you might use the strategy pattern. But today, we're going to focus a little bit more on implementation. So with that said, let's go ahead and dive in here. And just as a recap, the strategy design pattern, again, is a behavioral design pattern that enables us to select an algorithm at runtime. So again, we've looked at some tools in the previous lesson on how to do that, like using inheritance and runtime polymorphism, for instance, to call the right function. And we talked about some of the benefits. Again, you can check out the previous video for that. But again, the idea is that instead of hard coding and having a bunch of branches in our code, we can just select or exchange an algorithm at runtime. And we can also, of course, do this at compile time if you want to do stuff with templates. That is also an option that you can use to select algorithms based off of compile time parameters, but we're going to focus on runtime in this particular video. So one thing that we didn't look at last time is the actual pattern, how it's actually formalized. And if you read the famous design patterns book by the Gang of Four, or really any design pattern book, should have some diagram that looks something like this describing the strategy pattern. So above me here, you can see the hierarchy, and the strategy, this would be something like an interface to different sorting algorithms, and then we'd have an insertion sort here, a bubble sort, the actual implementations of this interface. And the context here, which is a little bit of a weird name, but basically context is the actual object that's using the pattern. So it's being fed in the actual data here. So we'll actually code that up in a moment here. But I want to actually give this in the context of an example, just so that we can sort of understand things. And I'm going to use a gaming example. So if you saw my previous videos linked in the playlist on the visitor, for instance, we looked at a particular game. I'd like to continue that theme here just to, again, provide some context as to when to use this pattern. So let's say that we have, again, some character in a game, maybe this orc here, and we want to figure out what type of combat strategy it's going to use. So we'd have some sort of orc class like this, and that is the context. And then our family of algorithms that we're going to choose from, which might be the combat strategies, which are highlighted here, are going to be what we choose when we actually do the actions here. Now, of course, things might be a little bit more interesting. Do actions might have other logic, but ultimately we just see that the combat strategy, so if I draw your attention to the left here, is just being called here to execute. There's no switch statement or if or any conditionals there. So with this example in mind, let's go ahead and just code this up from scratch here, just so we can understand how this pattern works. I'm going to go ahead and just open up a terminal here, and let's go ahead and write a simple example here for the strategy. Let's go ahead and include IOStream here. We're going to want to use the memory header here because I'm going to use unique pointer here for selecting our strategy. Okay, so first and foremost, let's go ahead and just create our object here, which is going to be an orc. And maybe we have a constructor for our orc and some way, again, to do actions. And this will set up our class here. So let's create one orc, and we'll call on our orc do actions. So whatever that might be, that might just be an update function that runs through the logic of your code in some application or business application, for instance. But that's the basic idea here. So again, what strategy is helping us avoid doing us here is basically saying if, some condition, we do something else, else if, and maybe many of these sort of conditions here, do something else here. Again, we don't want to have to embed all that logic here. We have something that's relatively dynamic, like a game that should change or respond to what players are doing, for instance. So again, we don't want to necessarily hard code that logic. So what we're going to do here is provide our strategy here, and I'm going to create an interface for that. And in particular, we're just going to call this combat. Okay, and I usually put a capital I in front just to indicate that it's an interface, not just a naming convention that I've used here. And let's go ahead and make the virtual destructor, since we're going to inherit from this particular class, just in case, again, there's anything that, this is basically the way to ensure the destructor gets called here for any of the derived classes. And then we're going to create our interface. So the function or behavior that we want to override, which I'm just going to call execute here, which means like do some action or whatever combat there is to do. Okay, so that's the basic idea here. So now our orc is actually going to hold as a member here, and I'll use a unique pointer here just to be a little bit better, safer C++ here. and we'll call this M combat strategy. And again, like all things, naming can be a little bit important here. So I also like to name things strategy, in part because it fits, but also it's just very explicit. Somebody searching around for strategy patterns would, recognize this. Okay, so now what I need to do here is let's go ahead and try to assign our orc a strategy. Maybe we want a default strategy here. Okay, so I could just assign it to a unique pointer here. So anything that is of type iCombat here. So we're going to want to do make unique, and let's try with iCombat. And let's go ahead and try to compile this. Now, some of you might already have red flags going off here. Will this compile? Well, it looks like it does compile, and I run it. But let's actually try to, we could use this class here. But again, remember with the strategy here, what we're missing here is we want to enforce this interface. And that's what's really going to help us perform the selection of different algorithms here. So I'm going to change this to a purely virtual function here. Okay, so that we do that in C++. That effectively makes this like a, in other languages, maybe like an abstract method you would put here as a keyword, but this is how we do it in C++. So now if I compile this, it is going to complain that, hey, you need to implement this actual function before we're able to call this later on here. Okay, so let's actually do that. Let's give ourselves, again, this is just the interface we want to enforce for different behaviors, i.e. the the part of the strategy pattern here. Okay, so this is going to be our family of related algorithms, which are going to be combat strategies. So again, just looking at this diagram here, let's go ahead to the UML. Right, this is the interface here that we've implemented, and now we want to actually implement some concrete strategies. So let's at least start with one here. Let's create a struct here. I'm just going to call this like no combat, and let's go ahead and we will use we will inherit from the combat. And then again, I need to implement this function here, execute. And I'm just going to go ahead and print out a message here for the class that's being called. So no combat, execute, just so we can see that it's being called here. And now I should be able to compile this. I still get the error here because we're instantiating from that interface that just has a abstract or purely virtual member function. So now we can actually do no combat, and I should be able to compile this and run it. Okay, so that is working now. We've set this up with our orc, and let's make sure that we can see all the code on our screen here. Let's go ahead and set this up here. And in our do actions, let's actually make sure that we do something with this strategy here. So what I'm actually going to do is just call that execute function, just so that we can see we have a default object that is, whenever we call do actions, executing the function here. Okay, so in this way, we've now got at least one concrete strategy here. Now we're not quite done though yet at this point. We haven't shown off the power of the strategy pattern, which is, well, I want to be able to change the actual actions that are done here. So I've got a few different design decisions that we can make here. So for instance, when we create our orc, we could pass in a strategy. I've just given it a default so that it has something to do whenever we call this execute, which I think is generally a good thing to do. But we probably want to have some way, again, to change this combat strategy. Now, I've made this a struct. It's public, which means we could access it. We probably want to make this private as far as being able to change the strategy here. So let's just go ahead and make it private. And anyways, where you can probably tell I'm going with this is we really want to write a setter function here for setting our strategy here. So I'm just going to call this set combat strategy. And then we need to pass in the combat strategy here. So this is going to be some unique pointer. Again, just matching the type that we have here for some type of combat here. Okay. And I'll just call this, C for combat here. And then basically what I need to do now, if I scroll down here, is set mcombat strategy to C here. Okay. Now let's test your C++ a little bit here. Again, if this is too much, if you haven't seen my videos on unique pointer, you can go check those out on YouTube. But let's see if this is going to work here. Okay, so let's go ahead and just try to let's try to just compile this much. And it is going to complain here. It's complaining about this line here, m combat strategy equals c. And this has to do with the unique pointer. If you have the shared pointer, it's not going to cause any problems, but unique pointer can't be copied. So we can't make a copy of this here, right? It has to be unique. So we need to change the ownership here. So what I'm going to do here is anything that we pass in to this function here, we want it to be an R value reference. And that means we need to make sure that this is movable into the combat strategy. Okay, so that I can assign or take over with this unique pointer the strategy. Okay, so that's going to be the basic idea. Now I can compile and I can run. Okay, and now that we have this way to inject or otherwise set the combat strategy here, I can actually use this function at runtime to change the strategies. Okay, so we're almost there. Let's go ahead and give ourselves just another strategy here, just so we can actually change it. Let's say there's I don't know, melee or something combat here. So let's do this from the melee combat. And then what will come back here is we'll have our orc do its actions, maybe some default actions. And then we're going to do orc set combat strategy. And I'm just going to create a new pointer here. So standard make unique. What kind of strategy do I want? Do I want this to be the melee combat? And let's go ahead and give that a try here. So we should see the no combat strategy, which is the default thing that we initialize our class with. And then we're going to call a new strategy and then continue to perform our actions while our program continues. Okay, so that is the basic idea. Let's go ahead and compile this. Compiles. Let's go ahead and run it. And now we can see that our different strategies are being called here. Okay, so let's just go ahead and, analyze this pattern for a little bit here. And then again, it becomes really easy. I mean, hopefully this is what you're taking away here. I have these combat strategies here that are, their own small little struct here, which is nice because then I can implement as many of these as I want. I could create some sort of plugin system where I could inherit from this class and have users or scripting languages add to this. So there's all sorts of interesting things that you could do here. My orc code all of a sudden becomes very, very clean here, right? It's just a set of executing basically the actions here. Okay, so this could generally be the case. You might have a little bit of conditional logic here, right? Like you might, for instance, be able to do the actions based off of, of course, if, orc is, their distance is less than 50 meters or something, right? So you might still have some conditional behavior here, but the point is I'm not implementing the whole, different logic for no combat, melee combat, range combat, all that type of stuff can be abstracted into here. So for instance, the melee combat, when I hit execute, it might not take place if the orc doesn't have a melee weapon, right? So they'll have to switch, and all that logic, so to speak, is handled in here. So again, it's a nice way to encapsulate all the things that are needed for that behavior in this, structure here. Or again, if you choose to do this in a more functional approach in a separate function. So that's kind of nice there. The other thing, again, that we observe here is, I can put these sort of actions here, like maybe I take these functions here, but this actual strategy or these patterns for doing actions, setting the combat, basically I can move that logic somewhere else in the program, in the actual game application logic. It doesn't have to all be embedded in the orc. The orc should only know about, sort of that it can do some sort of combat and that it's got its sort of attributes. So again, in this way, the strategy pattern really is a way to clean up code. You can argue that in a small enough project, again, none of these design patterns really matter, but as your project scales, again, it's nice to just be able to look at code like this and just see how it basically reads like the actions that are being done. Okay, so it's almost like a functional style here. And again, we get the flexibility to change at runtime with this set combat strategy. Now, as mentioned, you could template the orc if you wanted to make this more of a policy-based thing. And what that does is it basically, it limits your flexibility as far as what you could do at runtime in some ways. Again, you could combine and have some stuff at compile time, some at runtime. But the idea is that you could do that with compile time polymorphism as well. Now, the one thing to analyze and that some folks who maybe are performance minded might not like is this here, because we are adding a layer of indirection versus just calling, dot execute and having, something that isn't a pointer in memory. So we do pay a little bit of performance here. Again, with compile time polymorphism, you could compile that out if you're certain about what your orcs might be, and if they're not changing behaviors. Again, these are just design decisions that you have to make here. But overall, the flexibility that you get from being able to change the strategy at runtime to do more dynamic things in your program and overall kind of cleaning up your code is an advantage, I would say, with the strategy. Okay, so hopefully folks understand that. I'll scroll through the code one more time just in case you want to take a look. So here again is our interface. Here's our family of algorithms. Here is our orc, which holds on to the strategy, and then we can dynamically change that strategy at runtime, and then we just perform or delegate to whatever our strategy is in any of the member functions that make use of that strategy. So it's as simple as that. Not a super complicated pattern, as you can see. We've shown it in about 47 lines with comments and so on, but overall quite nice here. So anyways, this is what we looked at here, implementing our orc, just to again do a recap. So something like this is what we coded. Again, we can see where we hold the strategy and are able to execute. And again, you might want other ways to pass data into the actual orc, for instance. So for instance, your strategy here might actually take in some argument when you're executing, or maybe that is part of the orc class, like a handle to that object, which might reference the various attributes of the orc. Okay, so that's kind of leaning into a component-based system, which we will talk about on this channel, so stay tuned for that. But I just wanted to make a point of, if you have to pass parameters in these functions or look them up in some sort of global table or like a database, those are other things that you can do as well with your strategy. Okay, so I'll move out of the way here just so again you can see the connection. Here's the orc, which is our context. That's this side of the tree. And on this side of the tree is our strategy, which shows the family of related algorithms here. And I even added one more in the slides with range combat just for fun. Just so again you can see the flexibility of this pattern, which is quite nice. Now again, there are some different ways that you can think about passing in the strategy, and these are different types of injections, like there's constructor injection. We use something like a setter injection to inject the functionality in, and that's fine. And there are other ways you can also look up what strategies are available. There's a really neat service locator pattern. So that comes from a book, Game Programming Patterns, as well as other texts. But there's a really nice free write-up of here from the Game Programming Patterns book if you want to look that up. Because sometimes we might want to just look and see what strategies are available. Maybe they're being downloaded from the internet or whatever, and you want to just locate something or choose a strategy at random, for instance, for how these different objects are going to behave. So again, those are just some different ideas of different ways that you can assign strategies as well. All right, and then again, here is our code here. Okay, so we have our orc, we do our actions, maybe some time passes, you do another strategy, and then you do actions. And I guess I had in the slides, run away in fear is the no combat strategy that we'll print off. We're a little bit more fearful there. Alrighty, so in summary, this has been the strategy pattern. Hopefully you've enjoyed it. Here are a brief summary of pros and cons. There are a few more, but again, the strategy pattern, very useful for choosing your algorithm at runtime. Again, you can base that off of data that's in your application, resources available, making the behavior, again, more interesting. Potentially, I'd say that in most cases, the strategy makes your code more understandable because you're abstracting away those actions into separate objects. In this case, you also get the type safety from inheritance, which can be an advantage, and you can also lean into things like compile time polymorphism if you want to start getting into performance, but at least at a compile time have the ability to choose the strategy. Again, in a gaming example, it might not make as much sense in some cases, but you can think about other examples where you want to have sort of a compile time or maybe a series of types that you generate at compile time with different strategies that you just swap between. So again, different things that you can take a look at. Again, you always need to measure performance, but there is a layer of indirection that we've added with the strategy pattern. But again, maybe your compiler is smart enough to optimize away these types of things, but you have to measure first to know for sure. But anyways, when we pay a little bit of abstraction, that might clean up our code, or in many cases I found made it more easy to maintain our code, so the maintenance is a little bit better. We didn't test these strategies out, which I talked about as another main advantage of separating things out. So in general, I found strategy makes it easier to test the code, as well as it encourages me to do refactorings because it's easy to try a new strategy out. So that's just other sort of benefits here. Okay, so with that said, again, use the strategy pattern when you find yourself working with a family of algorithms. You have lots of switch statements or if else, long chains of those conditional statements. You again need to be able to change runtime behavior relatively dynamically or based off conditions. And again, you want more testable code. All right. So with that said, folks, thank you for your time and attention listening in on this video. I am going to point you to my other resources here. On my site here, I've posted or started posting my software design lessons here on courses.msha.io. So you can check those out. It's free. And these are just the same YouTube videos in a distraction-free environment, and you can track your progress on there and engage with the community. So anyways, folks, thank you for your time and attention. That's been the strategy pattern. I hope you've enjoyed it. I'll look forward to your discussion below. Let me know what you liked or disliked or different ways that you've been using it, or if you've done something with compile time or runtime with a strategy pattern that you think is interesting to share with the community. Alrighty, folks. Anyways, with that said, thanks again, and we'll see you in the next one.